Hello everyone, welcome to Learn Overflow. If you haven't subscribed to this channel, make sure you subscribe to this for regular LeetCode videos. So in this video, we will look into this problem, the kth largest element in an array. In the last video, I have already discussed two approaches to do this, but solve this particular question. The one is using a simple sorting of the array and then finding the kth greatest element. And the other one I was discussing was either using a heap. We can use either a min heap or a max heap. In that case as well, we come across to a solution that is n plus log n, one n being the traversing the whole array and log n being insertion into our min heap or the max heap. So that was the both ideas we have. The other option, the third like a third way to solve this problem is basically using another algorithm that is a quick select algorithm. So this video is I will explain about the quick select algorithm in details and how we can go ahead with this particular algorithm. And ultimately, we'll see how this algorithm ends up to be a better for us. So something we need to know over here that this quick select algorithm is more like our quick sort algorithm. Okay, like the partition part of our quick sort algorithm is exactly same to the partition part of our quick select algorithm. So this quick select algorithm is just a variation of our quick sort algorithm, and it is an optimized way to find the kth smallest or the kth largest element in an unsorted array. So yes, for us here we have an unsorted array as well. And why I mentioned unsorted array, because this quick select algorithm gives us an time complexity of order of n being the length of our array. Okay, but this is the average time complexity it gives to us. In case if we come across an worst case time complexity, in the worst case time complexity, it gives us an order of n square, that is worse than the other two methods we have discussed in our last video. So this algorithm is the best for when you have the average cases, but not the best when you have the worst case. So in a worst case, what can be the worst case? The worst case is when our array is actually sorted. So when our array is sorted, this would be our perfect, like a good complexity we'll get is an n square of like order of n square. Okay, we'll discuss how this kind of algorithm, like why this kind of complexity is coming for us, and we'll discuss in this step by step. So let's take our first example over here. So in the first example, we have an array. So we have an array that is this much element we have over here. Okay. So what we'll do, we'll go ahead and see how this particular algorithm works. So as I said, the first thing is we need to partition our array. What is the partitioning our array? Say we have an array like this, and the basic idea is we have elements over here. And what we want to do, we want to make this array in two parts. Like we want to break this array rather in two parts. Two parts being in the left part, we'll know that all the elements on the left is like less, okay, less than this particular array. Like all the elements on the left side of our partition will be less than all the elements on the right side of the partition. So we know for sure that all the elements on the right of this partition what we have created will be greater than all the elements on the left. So that was the idea behind this kind of partition. And we know in quick sort also we go ahead with particular this kind of like approach to our questions. Okay, so let's go ahead how we will go do this. To do this particular one, we'll start with our pivot element. Say we took 3, like the 0th position element as our pivot, or the lower point element as a pivot element. Okay, so what we will do exactly, we will say we took our this as a pivot. Okay, so then we need 2 pointers for us. What we will do, one pointer will be simply pointing, like say this is our left. So I'll say here our left pointer is pointing, here our right pointer is pointing. Okay, I'll just say left and right. And then, or you can say the low pointer or the high pointer is pointing at this position. So we just took left and right. So we're going to loop. And in this loop, what we'll do, we'll keep on checking that whatever the condition it is, this left should be less than our right point, right? And then the main idea, as I said, is to bring in all the elements that are less to our left hand side, or in all the elements to our right hand side. Okay. Now, the first thing we just go ahead, we just keep a check that our I pointer, a pointer which will help us to just swapping the elements, and our J pointer. So our J pointer will always be this left plus 1. So j pointer will be pointing at this position, okay? Initially. Initially, this will be the case for us. How will we go into this question? Is like we have two pointers over this question, as I say, and then we'll check that if the element at the jth position is less than element at the ith position, okay? If that is so, or not ith position, element at the low or the left hand or the pivot element that we got. So we took the pivot element as the leftmost element. So we'll check if the pivot element, if it is less than our pivot element, then what we do? We will first increment our I. Okay. So if that is so, so in this case, you can see that 2 is less than our 3. In that case, we will increment our I got here, and then we will swap elements with the jth position element with our ith position element. So in this case, what will happen? The swap will happen at the same position, and you will find the 2 being placed at this particular position, right? Then we'll check further, like after the swap, we will then move our j to the next position, increment our j, okay? So we incremented our j, and then we check again if the element on the left, okay, that is the left being pointing as 3, is less element on the left is greater than our right. So it was like the exact condition was the element on the jth position is less than element of the on the L. So if that is so, we found yes. So again, we will increment our I, right? We will increment our I over here. So we incremented our I and then swap the element of at the position j with the position I. So we find 1 being placed at this position. Okay. Next, look here. We then swapped our j, like moved our j to the next position. So j is now pointing at this position. So now we'll check element at j is less than our element as 3 or not. We find that no, element at j is not less than our element at the element at this low, right? So that is true. So in that case, we cannot swap the element. So we'll simply move ahead. We'll move to the increment of j to the next position. See, in that case, we are not moving our I, we're just moving our j to the next position. Okay. Now we moved our j. Next, we again check element at j is less than our element at low. Again, it is the false. So we moved our j to the next position. And then we check element as j less than our element as the element at low. So we find no, that is not true. And then we come out of the loop because we don't have any more elements for us. So j ran from this low plus 1 till less than equal to r. That is the rightmost element we have. So we came out of that and j pointed at somewhere here. So we have no element. So we just came out of the loop. Now we will swap where? We will swap this ith position element that we have over here with our low element. So what exactly happened for our case? So after this first run, like after this one iteration, what we find out, we just came across that our array looks more like this. 3, here is 1, here is 5, here is 6, here is 4. Okay. So this is more or less what our arrays looks like over here. Okay. Now, for sure, we know that this is the particular position that is being fixed for us, right? We don't need to look ahead that whether this element is for us or not, right? We got our element, to be honest. Like this element at position 3 is a pivot element, and we know that all the elements to its left of it are less than it, and all the elements to its right of it are greater than it. Okay. Now, what we need to see, we are not doing a sorting algorithm. It's not quick sort. It's like quick select algorithm. So here the algorithm changes. So till now we are just partitioning, and you can see is the exactly same thing we did. All the elements we did was like exactly same of the partition part. Now we'll check that our k element. What is our k? K being the number given to us. Okay. So our k is less than our I or not. Okay. Where is our I pointing? Remember, you need to do something over here. K given to us is a 2. What does 2 means? 2 means the second largest element, okay? But we are going from left hand side. So if we go check over here, we cannot find the actual answer. We need the largest element. So we need to change it to a index of the k largest, okay? So this is what is a kth largest. So we need to change it to an index of k largest before even doing so. What we'll do exactly? We'll say k equal to the length of the array, that is the 6, right, minus k. So we'll do something like this, k equal to length of the array minus k. So what it will give us? It will give us 4. So that means the fourth element would be our particular array, like the index 4 will be, or the fourth positioned array will be the particular for us. So look carefully. If we do this thing initially, what happens? So take it as a zero indexed element. Okay. So in the zero indexed element, it will be like 0, 1, 2, then 3, and then 4, and then 5. So what we know that whatever comes in this index will be our final answer, right? So now we can go ahead with our algorithm. What is it like? If our k, that is for now is 4, is greater than our is less than our I. So I is where I is pointing to index 2, right? And k is pointing here, right? So now we'll check if this is so, like k is less than I, false. If k is less than I, why would we have checked? We know that we need to check for the lower elements, like if that was so, like I was greater than k. But let's take this example and see here, and we'll talk in a later. So what exactly condition we have here is that I is less than k, right? So if we look carefully after the first run, what we found out that I is like I is pointing to an element that is sitting at its own place. That, like in a sorted array, that would be the original place that element will be sitting, right? So that's what I pointing to. Now we find that k is greater than our ith element. So what means, or what do we mean by that? We simply means that our kth element lies on the greater half of our array. That means we now need to check only with this elements. We don't have anything to do with the left hand side of our array. We just need to find out the right hand side. We need to point to a right hand side and find out where which is the particular array that we are searching for. And then again the same thing will run. We'll take a pointer over, like we now in the next case what will happen, we'll simply move our left to I plus 1. So our this left we have over here, so this left will move to I plus 1. That is our this left will be pointing at this position, our this right will be pointing at this position at the last. So we now have an array of like 5, 6 and 4. That's what our left and right is pointing to, and that's what we need to check for now. See, and then we'll go through the same process of ij being looping into there, finding out which one is less and which one is right, and then switching the like swapping the array we have over here. Basic idea, that's the thing. So after doing this, what we find that we will end up finding our this fourth index element, and we'll end up getting our particular solution. Now let's talk about the complexity we have over here. Okay, it may happen, just another note, it may happen that the ith element may also be the k being pointing to that position. So in that case, we will simply return this particular ith element. So that was the condition we have over here. Now let's consider this time complexity. What if our array was completely sorted? If our array was completely sorted, then after the first run, if our array is completely sorted, it would have a 1, 2, 3, 4, 5, and 6. I'm talking about the worst case complexity of this particular condition. Okay, so if our array has been this completely sorted for us, and we are doing a quick select on this, we'll take a first pointer as this, and then we find out whatever elements are left like lesser than this element, and we will find a check. So we found that none of the element is lesser than this, and we need to check the other half, that is a complete array without a single element, right? So in that case, what happens? We only keep on checking the whole array again and again and again. So it's more like if you remember exactly, it's more like t of n is basically we would end up like t of n minus 1, and then plus some constant time of like cn, like there's a constant time we get. So if we have something like this, so if we just remember our formulas to calculate this, then we end up happening like t of, or like order of n square, right? So that's the complexity we end up happening if our array is completely sorted. That's the worst case complexity. If in case on an average case complexity, what happens? See, we don't consider the whole array again and again. First time we consider our whole array, then we break the array in two parts, and then we consider the other half, like only a half of the array. So what that basically means, we have like t of n. Okay, so we have t of n. T of n will be something like t of n by 2 plus our constant time being calculating this, right? So that's how we have. So if we have like this t of n by 2, so if with like simple calculus, we know that it will end up ending in order of n, right? So it was more like a summation of n plus n by 2 plus n by 4, and like we'll end up doing this till we actually find the answer. So that's out of calculus we find that it's like order of n complexity we have over here. So that's what I said. Like on the worst case, we end up having an n square complexity, and on the average case, we end up having an order of n complexity. So this algorithm is a pretty good algorithm. So just now let's go ahead and write some code of following the particular algorithm, and post that I will explain what exactly I do and how the algorithm, like whatever I explain, how the stuff is being implemented in our code. All right. Now let's check what exactly we are doing over here. The first thing was exactly what I said. We were checking for like to convert our index to a index of k largest. Okay, so it was like initially given 2 over here. So we convert that. It will be we convert the value like the kth largest to our index value over our array. Okay, so we just ended up having this to be the 4 over here. So that will be pointing to the this position actually. So that's what we did over here. Now, then we have a low or high, low high being pointing to both the ends, and then a while loop for us, a while loop being pointing the low high part of for us. Okay. Now, as I said, we consider our I to be the low, and then we had our J being the low plus one. Remember, the I was pointing to the lowest element, and J was pointing to the next, like if our array was something like this, then I was pointing to a lowest element, and J was pointing to the next element. That was what we're doing, and that still we are. If it was like low over here, then right over here. Okay, so that's how we were doing that. We'll keep checking. So that's the condition. Like if the value of the jth position is less than the low that the position at this, then we increment I plus first. That's I plus plus I. So it will increment I first, and then swap the elements. So swap will end up having the same position over here, right? Both being at the same position, and then if that is not so, then we'll just increment I, sorry, increment J. If that is not so, J will keep incrementing. And then after like the whole swap is done, a particular like a complete loop is done for us. We like we swap the I position element with the low position element. Okay, so that's the idea behind this. And then like this was our partition condition that we usually have to just point our pivot element, that is a low element, to the position it should actually exist. Okay, so that was the idea behind that. Now after that, this was the additional stuff we do in our quick select. Was that we check that if the k now pointing to the particular index we want to do, if a k is less than I, so I being on the right side, that means we need to check on the left half of the pivot element. So that's the we need to check for the left half. So we just move a high to the left, being the I being the pivot element. So kindly point to the pivot position. So it's like I minus one. And if it's like on the right, that means the k is greater than I. So that means we should check on the right hand side of the array. So we just make our low move to the I plus one. That was what I was explaining exactly. And in case we just found out that k is equal to I, okay, not the less, not right, but rather k is equal to I, then we know that this is a particular element that we are searching for. So we found out our element, and that should be returned. And then there is a condition like actually this shouldn't be executing ever, but rather you need to return to that if k is invalid, or like somehow k is not a valid number, or we don't like k is something, say minus one, minus two. That's not a particular array index, right? That's invalid stuff. So we ended up returning minus one as an just a note. But on a like if the question goes exactly what the question says, like k will be from 1 to 10 to the power 4, so this won't happen. But since we have a return type over here, and our compiler won't run without a final return type, our this return value is within our while statement. So once the while statement is break, we need to give some return statement. So that's the we just give a like a dummy return statement, you can say. And this is the swap element we have, like swapping the elements. Only those index elements are being swapped. And then you can see you just now saw that this question is actually got accepted for us. So that's all for this video, guys. So I hope you like this explanation of this quick select element. And for this, if you think there is anything I missed out, or if there is you have still some doubts for your left, make sure you just comment down your doubts. And we'll see in our next video. Also, like this video, that gives a lot of motivation to us, like to me, to create more videos like this. Also, subscribe to this channel if you haven't subscribed yet. Thank you all for watching this video. Hope to see you soon in my next video.